This is day 17 of Advent of Cyber 2023, and this challenge is called I Taught, I Tore a C2 Tat. Congratulations, you made it to day 17. The story, however, is just getting started. There are more things to discover, examine, and analyze. Until now, you have worked with multiple events, including prompt injection, log analysis, brute force, data recovery, exploitation, data exfiltration, suspicious drives, malware injection, account takeover, phishing, and machine learning concepts. Yes, there are tons of anomalies, indicators of attack, and indicators of compromise. Santa's Security Operations Center needs to see the big picture to identify scope, prioritize, and evaluate these anomalies in order to manage the ongoing situation effectively. So how can we zoom out a bit and create a timeline to see the investigation's initial boundaries and scope? McSkitty decides to focus on network statistics. When there are many network artifacts, it's a good choice to consider network in and out, as well as load statistics to create hypotheses. Now it's time to help the SSOC team by quickly checking network traffic statistics to gain insight into the ongoing madness. Let's go. So for this challenge, we need to open up the virtual machine, and we can then open it as in the split view. So the virtual machine contains a fresh version of Silk. It has the required artifacts to work on, so when that's loaded up and we get through all this, we can get started on it. So the learning objectives are to gain knowledge of the network traffic data format, understand the differences between full packet captures and network flows, learn how to process network flow data, discover the Silk tool suite, and gain hands-on experience in network flow analysis with Silk. So the network traffic, the network data is everywhere. It is all around us, even now in this very task. Network communication and traffic are the natural behaviors of today's interconnected computed world. These behaviors represent a constant data flow of daily activities, including personal interactions and business transactions. The data flow offers invaluable network management, troubleshooting, incident response, and threat hunting insights. The table below highlights the importance and key benefits of each of these aspects. So, network management, monitoring network performance, identifying bandwidth bottlenecks, and ensuring resource allocation and quality of service. Troubleshooting, identifying network issues, latency and connectivity, validating configuration implementations and changes, and setting performance baselines. Incident response, incident scope, root cause analysis, and assessment of the compliance aspects of incidents and day-to-day operations. Then threat hunting, proactive analysis of signs of suspicious and malicious patterns, potential threats, anomalies, and IOCs. Also, behavioral analysis is used to detect intrusions and insider threats. Network traffic comes in various data types and formats. Packet capture PCAP format is the first thing that comes to mind. It provides a granular, raw, and comprehensive view of the network traffic. This format provides all possible data represented in packets in a ready-to-investigate format, the approach also known as deep packet inspection. Therefore, it is an invaluable artifact for network-level operations. However, this intensive resource needs storage, processing, and analysis capacities to provide comprehensive insight into network traffic. In other words, while PCAPs are very useful for detailed analysis, they are not practical for fast analysis situations as they enclose the actual payload. This situation becomes a pain point when large amounts of data need to be analyzed. The data richness and level of detail provided by the PCAP format come from the payload it carries. At this point, it will be possible to speed up the process considerably by running the analysis process on a data format that doesn't enclose the payload data. As a result, it will be possible to process more data in a shorter time with fewer resources, leaving more time for analysis and decision making. Network flow data is a lightweight alternative to PCAPs. It's commonly used in NetFlow format, a telemetry protocol developed by Cisco that focuses on the metadata part of the traffic. In other words, it provides only the summary of the traffic. The details appear similarly to how call details appear on your phone bill. Once again, there are no packet content details with this format. This is why storing, processing, and analyzing the data format is easier than it is with PCAPs. It looks like this data format will help the team accomplish the task McSkitty assigned to them. A closer look at PCAPs and flows. Let's take a close look at these two formats to see how they differ and understand what to expect from each one. If you're still unfamiliar with networking terminology and the basics of this task, you can always get help from the rooms in the Network Fundamentals module. So feature, model, PCAP is packet capture, network flows, protocol flow records, depth of information, detailed granular data contains the packet details and payload, and then network flows summary data doesn't contain the packet details and payload. The main purpose is for deep packet analytics for PCAP, and then summary of the traffic flow for network flow. The pros provides high visibility of packet details, while network flow provides a high-level summary of the big picture. Encryption is not an obstacle. And the cons, PCAP's hard to process and requires time and resources to store and analyze. Encryption is an obstacle. And the con for network flow is that you only get the summary and no payload. And then with PCAP, you can get the layer headers and payload data, while network flow you get the packet metadata. The table above highlights the conceptual differences between PCAP and network flow at a high level. Now let's get into a more technical comparison of these two formats, and understand why McSkitty chose this approach as a quick solution for understanding overall network traffic activities. L. Forensic McBloy explains the differences in the tables below. So the key data files are PCAP format, get link, layer information, timestamps, packet length, MAC addresses, both source and destination, IP and port information, both source and destination, TCP and UDP information, application layer protocol details, and packet data and payload. While the key data fields of network flow format, you get IP and port information, both source and destination, protocol use, volume details in byte and packet metrics, TCP flags, time details such as start, duration, end time. You get sensor information and application layer protocol information. Forensic McBloy explains that the significant difference between PCAPs and network flows is the packet detail visibility and processing speed. Remember, McSkitty wants the statistics as soon as possible. You'll help the SSOC team work on network flows. So how to collect and process network data. Network data collection and processing typically involves using network monitoring and analysis tools, such as Wireshark, T-Sharp, and TCP dump, to collect information about the traffic on a network and then analyze that data to gain insight, troubleshoot, or conduct blue and purple team operations. Also, product and system-based solutions will help collect network data in flow format. The specific tools and methods you will use will depend on the size and complexity of your network and your objectives. If you would like to learn more about the network data capturing and analysis processes, the Wireshark module can help you get started. The SSOC team tells us they have some PCAPs and network flow records, but the available data needs to be more organized and ready for analysis. Luckily, one of the team members remembered a suggestion from McSkitty. Hints from McSkitty. You can collect network flows from endpoints and network devices in the same way as you collect full packet captures. It's also possible to convert PCAPs to network flows if you need a quick look at network statistics on a pre-recorded file. Many open source tools can help you read network flows or convert PCAPs to network flow data, and Silk is one of the most popular choices. And good news, L. Forensic McBloy has converted all the network traffic data to binary flow format. We still need to discover how to analyze it. Follow up on recommendations and exploration of tools. Let's continue with McSkitty's suggestion. Explore and use Silk to help SSOC in this task. Silk, or the System for Internet Level Knowledge tool suite, was developed by CERT Situational Awareness Group at Carnegie Mellon University Software Engineering Institute. It contains various tools and binaries that allow users to collect, parse, filter, and analyze network traffic data. In other words, Silk helps analysts gain insight into multiple aspects of network behavior. Silk can process direct flows, PCAP files, and binary flow data. In this task, you'll experiment using Silk tools on binary formats to help the SSOC team achieve their goals. Elflog McBloy gives us the network flow data in a binary format, so we have enough data sources to get to work. So first I'm going to open up in split view, and then go to full screen just so it's easier for us, and I'll go back down to here. So getting started with Silk Suite. The Silk Suite has two parts, the packing system and the analysis suite. The packing system supports the collection of multiple network flow types, IPFix, NetFlow version 9 and NetFlow version 5, and stores them in binary formats. The analysis suite contains the tools needed to carry out various operations, list, sort, count, and statistics on network flow records. The analysis tools also support Linux CLI pipes, allowing you to create sophisticated queries. The VM contains a binary flow file, suspiciousflows.silk, in the desktop directory. You can verify this by clicking the terminal icon on the desktop and executing the following commands: cd desktop, then ll, and you'll get a list of all the files in the directory, suspicious flows. So let's do that. Although we can see on the device right here, it's in the desktop, but because we're probably going to be using the terminal anyway, we will cd into desktop, and then ll. In case you don't know, ll is ls-l. Actually no, it's doing ls-la. So ll is just a shortcut for that. The next step is discovering the details of the pre-installed Silk instance in the VM. Use the commands provided to verify the Silk Suite's installation. Use the following command to verify and view the installation details. So we'll run silk-config-v. Oops, I spelled that incorrectly. Get rid of that last V there. Silk, okay, apparently it's not found. Underscore silk_config-v. There we go. So we got version 3.19.1 there. And while we're at it, we may as well take a look at the questions asked, because which version of Silk is installed? That version is 3.19.1. And we may as well just take a look at the questions as we go on. Okay, so Silk mainly works on a data repository, but it can also process data sources not in the base data repository. By default, the data repository resides under the var silk data directory, which can be changed by updating the Silk's main configuration file. Note that this task's primary focus is using the Silk suite for analysis. Therefore, we'll only use the network flows given by the SSOC team. Quick win that will help you answer the question. You now know which Silk version you are using, which we already answered. Flow file properties with Silk suite. RW file info. One of the top 5 actions in packet and flow analysis is overviewing the file info. Silk suite has a tool, RW file info, that makes this possible. Now let's start working with the artifacts provided. We'll need to view the details of the binary flow files using the command below. So that will be on the desktop here. So the command is the RW file info and then suspicious flows. So what does this tell us? We can see it's IPv6 routing, 11774 records, and I think that count records was question 2. So if we go down here, 11774, and we now have the size of the flows. So this tool helps you discover the file's high level details. Now you should see the Silk version, header, length, and total number of flow records and file size. And it's saying again that this also helps with answering question. So reading flow files, RW cut. RW cut reads binary flow records and prints those selected by the user in text format. It works like reading and filtering tool. For instance, you can open and print all the records without any filter or parameter, as shown in the command and terminal below. So RW cut file name. So we'll do RW cut suspicious flows.silk, and it's given us a lot of output, and it's telling us to use the flag --num --num.--rex equals 5. So display 5 records, which we have now done. You can also do tail-rex to get the last one. So the information we have, actually probably easier to look at this one. So source IP, destination IP, source port, destination port. Not sure what these two are. Bytes, the size of the records, or the traffic, which flags are used, source time, duration, and then end time. So it's giving us another command to only get the information that we want. So just to make it easier, we will copy and paste it, and then paste that here, and we'll run that. And we actually need to put in the file name, which is suspiciousflows.silk. So suspicious-flows.silk, and we can see we've now got the information we want. So source IP, maybe I need to expand this more. Okay, there we go, we can see things a bit more clearly. So source IP port, then destination IP port. So it gives us a description of all things that it's showing. One more detail to pay attention to before proceeding. Look at it again at the RW cut terminal above and check the protocol pro column. You should have noticed the numeric values under the protocol section. This column shows the used protocol in decimal format. You'll need to pay attention to this section as Silk highlights protocols in binary form, i.e. 6 or 17, not in keywords, TCP or UDP. So hints from Forensic in the blue. In the forensics aspect of network traffic, every detail is represented by numerical values. To master network traffic and packet analysis, you must have a solid knowledge of protocol numbers, including decimal and hex representations. Note that IANA assigns internet protocol numbers, so ICMP is 4, IPv4 is 4, TCP is 6, and UDP is 17. So we can now answer a question for the date of the 6th record. So if we go back to the previous one, actually we can go to here, and which field is it that we want to get? So it's date. Change this to 6 records, and we will add in S time, and it's the 5th of December 2023. So we'll now go down to the questions. What's the start time? So we will copy all that. We'll grab it from here now and paste it in. And that is the 6th record. So you need to change it so you grab 6. And what is the destination port of the 6th record, UDP record? So UDP was 17, was it? Okay, yeah, UDP 17. And scrolling down from here, we can see we can actually pass in options for our specific value types. So we'll rerun that, and I think we could do --proto equals 17. Nope, is that wrong? Okay, so that's for our filter, so we'll need to continue reading a little bit. So filtering the event of interest, RW filter. We've covered how to read and filter particular columns with RW cut, but we need to implement conditional filters to extract specific records from the flow. RW filter would help us implement conditional and logical filters to extract records for the event of interest. RW filter is an essential part of the Silk suite. It comes with multiple filters for each column in the sample you're working on and is vital for conducting impactful flow analysis. However, even though RW filter is essential and powerful, it has a tricky detail. It requires its output to be post-processed. This means that it doesn't display the result on the terminal, and as such, it's most commonly used with RWCut to view the output. So view the examples below. So you do RW filter on that and it does nothing. But then in this example here, RW filter on the file, you make the protocol UDP and then you pass it the standard output, then you pipe that to RWCut to show 5 records. So let's copy and paste this into here, and we'll also need to change the file name again, and that file is suspicious-flows.silk. Now we've got the top 5 records that are UDP, but the question that we wanted answered was the 6th record. So we'll go back down here, destination port of the 6th UDP one. Destination port is 49950. In case you didn't see that, it's this number here. Now see, what is the record value percentage of the destination port 53? Okay, that looks like it's going to be using another tool, so we'll go back up to here. Okay, so quick statistics, RW stats. Up to this point, we have covered fundamental tools that help provide some statistics on traffic records. It's now time to speed things up for a quicker, more automated view of the events. Before you start to work with RW stats, you need to remember how to use the -- fields parameter we covered in the rfilter section to fire alternative filtering commands for the event of interest. If you need help using the parameters, return to the RW filter section and practice using the parameters provided. If you are comfortable with the previous tools, let's move on and discover the power of statistics. So I've got this example command. So RW stats, you're setting the fields, so destination port, doing statistics on the destination port, and the values, records, packets, bytes, etc. And count equals 10. So it's only going to print 10 records to the console. So using these fields as the measurement. And then for this, it's going to show the number of unique IP addresses that use the filtered field. So if we now copy and paste this command in, and also making sure to change the file name. So if we now run that, apparently RW is not found. It's because, my bad, I accidentally removed an S from there. So go to here, put the S back in. Oh, I also spelled that wrong. S. There we go. Okay, what I might do is just zoom out a little bit, and then expand this. There we go, that's a bit easier to see. So destination port 53 is 35% of the records. So that was the next question. 35.332.332.088. That's correct. What is the number of bytes transmitted by the top talker on the network? We will find out in the next section. So assemble the toolset and start hunting anomalies. Congratulations, you have all the necessary tools and have completed all the necessary preparation steps. Now it's time to use what you have learned and save Christmas. Start by listing the top talkers on the network. So if we grab this one, we're doing the stats on it based on the source IP, and then also grabbing the values for bytes. And we're grabbing the top 10 talkers. So copy that, paste that here, change the file. So now if we run that, we can see that the most traffic came from this IP address, and they did 735,000 bytes. So if we go back to the next question, number of bytes transmitted, 735,229. If you see the next question, what is the S-time value of the first DNS record going to port 53? So let's go to a previous command. That would be rwcut. Actually, that will be rfilter. And let's see if we can do dport equals 53. Is that something we can do? Nope, that is not. So maybe we've actually missed something for that, because that wasn't working. So that's okay. Apparently, okay, a port 80. Okay, maybe we just need to do a port instead of dport. And for the sake of trying, let's do lowercase, because that could actually be it. Okay, there we go. So lowercase is what it is. And what did the question want? The S time of the first DNS record. So that would be, which one is that? This one, I think. So let's copy that and paste into here. So that's correct. What is the IP address of the host that the C2 potentially controls? So I'm not sure how we're meant to find that, so maybe we need to just go through here and take a look. Okay, so what I think it wants us to do is look at traffic using port 53 and look at which IP addresses are using it the most. So we'll grab this, but we'll change it to a port just so it's all traffic, and we'll just copy this because it's easier, but and also looking at the IP addresses and then information that's actually needed. So paste that here, then paste that here. Oh, two pipes. So get rid of that second one. Run that. As we can see, there are two IP addresses which have done a ton of port 53 traffic. So what was the question? What is the IP address of the host that the C2 potentially controls? Looking at this, I'm going to take a guess and say it's the bottom one because there's greater data being sent to port 53, which I wouldn't have thought would be the case. You'd think that the one with the more records would have the more data. So copy that, and it wants us to defang it, so you put square braces around the dots so you don't accidentally click on the link, the IP address. That's not the one, so maybe it is the second one. So we'll just read that from there. So we need to go 175, 175, 175, 173, 221. Okay, it's that one. So which IP address is suspected to be the flood attacker? So we'll probably need to go back up here and to figure that one out. So what we'll do is grab this one, which is looking at port 80 requests. So paste that to there, paste that to here, run that, and we must not forget to change the file name, suspicious-flows.silk. And we have two IP addresses which make a bunch of requests to each other. So that's most likely the first one that is making those requests. So copy that, put that into here, and defang it once again. Nope, that's not the IP address. I just assumed that was the command for this. So back over to here, those two IP addresses are making noise, but what we really should be doing is passing this output and getting some stats on it. So we'll remove the original stats that we're getting, and we'll paste this one in. And what we are doing, accidentally kept too much in there. So we run that, and we see that this IP address is doing the most traffic, and this one is most likely, so this one is the server. As you can see, it's sending it to these IP addresses, which most likely just like web browsers or something, being used temporarily. So we've now listed all the IP addresses that use port 80 and revealed that the address ending in 236.223 was one that created the noise by sending requests. So we don't have the payload to see the request details, but the flow can give some insights about the pattern. So let's view the frequency. So we are going to copy all of this, paste that to here, and I'm just going to suspicious-flows.silk, do that in there because it's nice and quick. Now paste that into here. Apparently the pipe broke for standard output. Okay, what, did I do something wrong with this? Maybe if we get rid of head, that does something. Okay, we'll do that. And instead of head, probably just filter it down to number of records. That's what we'll do. We're using rcut, so -num-rex equals 10. Okay, so we'll go back to where we were. So as we can see, it's in the flags column, a bunch of SYN packets are being sent from this address to this one. And doing this is a SYN flood attack, which is a form of denial of service, where you just send a ton of flags to the server, and basically it's trying to respond to it in the SYN-ACK triple handshake. So basically it's just flooding the server with SYN requests. The server then makes the SYN-ACK request back, but we're not responding to it, we're just sending more SYN, which is then responding to. So, which IP address did I put before? Okay, I put the wrong one there. It's meant to be 6. So submit that. So now we need to find out how many were being sent. So to find out how many were being sent, we can take a look at this command right here. So filtering based on the source IP address, passing it out, and we are filtering, performing stats based on the source IP, flag, and destination IP. So we'll paste that here, change the file name, and paste that into here. And we can see 1658 requests were made from this IP address to this one, and they all just had the SYN flag. So we know that's 1658 requests were made in this flooding attack. So 1658, and that is day 17 completed. If you like this video, make sure to like and subscribe so you can watch me complete the rest of these Advent of Cyber 2023 challenges.